All right, so we continue our discussion of what conditions can ensure the convergence of series. We've applied certain principles and certain results for general sequences to the study of series because series, series come from partial sums of a sequence, which in these partial sums constitute sequences in their own right. And so we've basically just rewritten some of these results that were stated for general sequences in the language of series. I mean, how they look like when we apply them to series, like the Cauchy criterion. And we also made use of the Cauchy criterion for series, and we've also made use of the the least upper bound property to show convergence of series, provided that the term by term, uh, term by term, there are you have two sequences, and one of them bounds the one another one from above if the terms are positive, and if the larger sum is convergent, that means that the series that they bound is also convergent. Remember, this is just one of the last things we saw. This just requires all the terms to be positive. In fact, you don't actually need that all the terms are positive. Everything plays out for large values of n anyway when you're considering the partial sums. So you can basically ignore what happens for as many as you want, as long as they're fixed and a fixed number of the terms. You can forget what happens about what happens with them, and as long as the terms are non-negative from point on, then the same theorem applies. So in the same way, I mean, maybe you have two sequences A sub k and B sub k. Maybe B sub k is not always greater than or equal to AK, but if that statement is true, say for values of k greater than a million, then you're fine. I mean, you can apply the same principle. Okay, so it's as long as all the properties all the hypotheses that are required in all the previous theorems are violated for finitely many terms, then everything else applies. Remember that everything for sequences and series happens at the tails. That's what's really important. Uh, we saw a very important series which we had already discussed before, which is the geometric series. This is a series that's gonna be used to prove convergence of other series. And in fact, all the tests that you know for the convergent of power series, for instance, the ratio test, the root test, all of those come from comparing series with geometric series. The good thing about the geometric series is that the uh, the actual value of the series when when uh, you can actually find a value for it. So when the series is convergent, can be made explicit. And all the computations are explicit, so you have a very clear threshold. So we saw it before that when the absolute value of the absolute value of r is less than 1, then the series is convergent, and if not, then the series is divergent. And it's divergent, I mean, we covered everything except for the case when r is equal to -1. We started with the case when r is equal to 1, and then we saw what happened when the absolute value of r was less than 1, in which case the series was convergent. If not, then it was divergent. But in the case when a is when r is equal to -1, say, what we have is a series that looks like this: a minus a, a minus a plus a minus a plus a. And of course, this doesn't converge. If you consider, you know, even terms, so if you consider odd terms, you have a, then you have a again, a minus a plus a is a, then a minus a is 0, a minus a is 0, then you have a again. So for the odd terms give you a. Well, all the all the um, all the even terms in the partial sum sequence give you 0, 0, and then of course if you have another term here, it gives you 0 as well. So you have two subsequences that are converting to perhaps different numbers. The only way that one is converting to a is actually equal to a, and the other one is equal to 0. So these subsequences will be equal to each other only if a is equal to 0. So again, we're at the point where the corresponding series will converge if and only if a is equal to 0. You can check by hand that when you see a requirement that on one side, if the series converges, then a must be 0. But you can check directly that if a is 0, then the series converges. So you have now we have completely classified the convergence of geometric series. We have a test that allows us to compare series and to see whether they and to know and to be able to conclude that if we have one convergent series and bounce another one from above, so all the partial sums are bounded by the partial sums of the convergent series, then in the terms of non-negative, then we can conclude that then both series are convergent, not just the one we already knew about, but the other one as well, the one that is bounded by this other extra, this other series. So now we have sorry. The absolute convergence test and this is something that is of course important also for applications. I mean, remember that we're gathering certain properties that will allow us to conclude whether a series is converging or not based on the convergence of some other series. And of course, I mean, once we know we have examples like the case of the geometric series, we can know for sure, I mean, whether it's convergent or not. Then we're going to be using these series with these properties to be able to conclude the convergence or divergence of other series. So the absolute convergence test is something that is very powerful, and the idea is actually very simple. We have if the series sum from n equals 1 to infinity of the of certain terms an, the absolute value of some an's. So if that is convergent, then the series without the absolute values is also convergent. So the condition that the sum of the absolute values of an, absolute value of the an's converge, uh, converges is a stronger statement than just saying that the sum of the an's converges. um, so what is the idea here? The idea is that if I mean some elementary process, it's just a triangle inequality again. Well, the thing is, if you wanted to test convergence, I mean, since remember what I told you, you write down. Well, I mean, let's just use the Cauchy criterion. So from the Cauchy criterion for series, we know that for all epsilon greater than 0, there is an n in n such that for all n greater than m greater than or equal to n, the absolute value of the terms in this sequence here, I mean the absolute value of the sum of the terms in this sequence from m plus 1 up to n is bounded from above by epsilon. So sum of the base of k, say, this is just the Cauchy criterion. I mean, the series is convergent, so the associated partial sum must be Cauchy sequence. And this is the Cauchy criterion, which we covered in the previous video. So now, what do we want? We want to show the same thing. So for all epsilon greater than 0, there is an n, such that for all n and m, such that n is greater than m is greater than or equal to n. This is less than epsilon, where we actually remove the absolute values. Well, that's going to be very simple, because here, I mean, this quantity here is greater than or equal to the absolute value, the sum of the AKs. This is just a triangular inequality. We have that the sum of the AKs in absolute value from k equals n plus 1 up to n is less than or equal to the sum of the absolute values of the AKs. Here the inequality is not as strict. I mean, if all the AKs are positive, then those two expressions will be the same. If there are some terms with opposite signs, then this is probably, and this is not going to be this is not going to be the same. What's on the right hand side is not going to be the same to what you have on the left hand side. But we know that this, okay, going back to what we want to show, this is less than epsilon. So we actually found that to prove the convergence of the AK, the sum of the AKs of the series of the for the AKs, so what we've shown is that given an epsilon, we need to find. I mean, we can show that the partial sums of the AKs constitute a Cauchy sequence. And to do that, we use the fact that the sum of the absolute values of the ends is a Cauchy sequence. I mean, the partial sums of the absolute values of the ends is a Cauchy sequence because we're assuming that the series converges. And we find out that whenever you're given an epsilon, you can use exactly the same n, capital N, that you use for the sum of the absolute values of the ends. And you can conclude then the desired Cauchy criterion. I mean, this property that the elements in subsets of the tail are really small when you add them all together. Okay, so the Cauchy criterion also to conclude then that the series converges as well. Okay. Naturally, and this is kind of what motivates the introduction of the harmonic series and this alternating series of the 1 minus 1 over 2 plus 1 third minus 1 fourth, etc. Is because this is it's a way of warning you about, I mean, some things you may be tempted to say. For instance, like in the we saw in the previous video, that that if something in a series, we already know that thanks to the previous video, that if the sum of some ANs exists, meaning that the series is convergent, then the ANs go to 0. However, the converse is not true. If you have a sequence of ANs converging to 0, it needs not be the case that you can add them and obtain a number. Maybe the series is divergent, and this example comes from the harmonic series. I mean, the first thing you should think about, I mean, they're not the only examples, but the first thing you should think about is the harmonic series. Well, these are the statements. I mean, these kinds of statements about convergence. I mean, the converse statements are violated usually by the harmonic series. And here there is something to be said about this, because you see, this is a clear example that if this converges, I mean the converse, if this converges, you cannot conclude that then this converges as well. We already know that 1 minus 1 half plus 1 third minus 1 fourth, etc., that converges. We already know that. However, the sum of the absolute values, meaning the sum of 1 plus 1 half plus 1 third, etc., diverges. You can use the test that we learned not long ago. The sum of the, since the 1 over n are decreasing, so 1 over n is a decreasing sequence. When you add them together to check for convergence, it suffices to consider the divergence or convergence of the sum of 2 to the k's or times 1 over 2 to the k. It gives you 1. Since that adding 1 infinity many times gives you infinity, that series is not convergent. So while we have that this the alternating series is convergent, you cannot conclude that the harmonic series, so adding all the 1 over n for n for all n in n, is not convergent. So the implication really goes in this direction. If you can add the absolute values and obtain something finite, then you can add the terms themselves and obtain something. So the series is convergent. But not the other way around. Now, again, connecting to the same discussion, we have the theorem 2.7.7, which is the alternating series test. So in this case, we have some AN. We're given a sequence. Satisfying two things. The first one is that the sequence is not increasing, so a sub 1 is greater than or equal to a sub 2, greater than or equal to a sub 3, etc. And the second one is that the limit of the AN, limit of AN as n goes to infinity is equal to 0. Okay, so we have the two conditions. So this is, it may seem that I'm contradicting myself now, but no. But I mean, whether this implication holds. But no, I mean, no, not this implication. The implication in one of the previous theorems when we said that the nth term of a convergent series must go to 0. Now we have a sequence that goes to 0 and a corresponding series that will converge. However, there are two differences. No, there's one difference. First of all, there's one big difference. Even though we assume that the ANs go to 0, we are not going to be adding the ANs, but instead we're going to be adding the term sign minus 1 to the n plus 1. So the series alternates in sign, and we also need to assume that the sequence is not increasing. It's not such a bad thing, but this is actually really important. Without it, we cannot conclude the theorem. This is not just something that simplifies the proof or anything, but something that is really necessary. So here the conclusion is then the series converges. In general, as I said, if AN is a sequence that converges to 0, you cannot conclude that it's a sequence. Yeah, sequence converges to 0. You cannot conclude the series made of adding these terms necessarily converges. But if you have a sequence that is not increasing, and in addition the nth term goes to 0, then you can conclude that if you alternate the signs of the ANs, so you consider minus 1 the n plus 1 times a sub n and add all these numbers, and in this very order, no reordering is allowed, then that converges. Again, I mean, this goes, this again brings us back to the example, the example from the beginning of our discussion about sequences and series. So the alternating expression 1 minus 1/2 plus 1/3 and etc. and so on was something that motivated us at the beginning, and it's one of those examples where you can tie in with several different aspects of all the theory of convergence of series. So there are examples here. So one example is this one, the alternating series test. This other test, the absolute convergence test, and all these other considerations that we just discussed in the last few minutes. So now, okay, we can conclude certainly that this alternating series converges, and the proof is going to be left for you as an exercise. It's a very good exercise. In fact, it's given to you as an exercise in the book and the book as well. And the idea is that you can show that the sequence is Cauchy. Once you show that it is Cauchy, then you will certainly have shown that the sequence is convergent because of the Cauchy criterion. And how do you do that? Well, you know that if we add, so think about it, yeah, so you can think about it this way. So you're going to be adding certain numbers, an plus minus an plus 1, plus so n plus 2, etc. Well, this is actually bounded. This is going to be bounded. So we add, say this is not, it's just a discussion. So you have an, let's choose a different letter. Am minus am plus 1 plus am plus 2 plus minus am plus 3 minus am plus 4, and up to a certain value up here. Well, you can, yeah, so some an, it could be minus an, depending on whether n is odd or even. But let's look at this. Let's look at this sum here for now. So you know that the sequence is not increasing. So this means that this is less than or equal to 0. This is less than or equal to 0. And depending on where you end the sum, this is going to be less than or equal to a sub m. Right, because you're subtracting something when you group the terms in this way. And notice here that, well, at the most, you're going to have, if the last term is a negative term, you're going to have an am and an an. But since am is greater than or equal to an because of assumption I, what you're going to be able to say is that this is going to be less than a sub m. And remember, what we're assuming here is that this goes to 0. So this tail here is going to 0, which is exactly what we need for the Cauchy criterion. And how do we know that, well, this allows us to conclude, because of course, if you have something that goes to 0, bounds minus 3 from above, it doesn't say that this is, it doesn't imply that this goes to 0. Well, it does, because yeah, so you have this tail bounded by something, so say 2 am, which goes to 0. And of course, this is going to be, since you're only subtracting terms, this is going to be less than or equal to am minus the previous element, so say a sub m minus 1. So this whole thing goes to 0, and in the same way, maybe we need to shift things in the argument, but this thing is going to go to 0 as well. And so this goes to 0, and this the left hand side here goes to 0, so by the squeeze theorem the thing in the middle goes to 0. Okay, so this is what tells you that an alternating series converges. Remember that knowing, I mean, we don't know the limit, but we know it converges, and that's because if I have a Cauchy sequence, we know that will be convergent, and that's thanks to the least upper bound property. So this is a non-constructive proof of the limit, of the existence of a limit to such a series, an alternating series like that. It is worth noticing again, I said this is going to be less than that, less than that. It's going to be worth noticing that these two conditions imply that all the ANs are greater than or equal to 0. Why? Because if at some point some AM were to be negative, then this implies that A sub M plus 1 is going to be less than or equal to A sub M, which is some number alpha. So you will be subtracting alpha. No, not subtracting. You have terms that are more negative than alpha, so that cannot possibly converge to 0. So if you want something to converge to 0, then it must approach 0. It must be in any neighborhood of 0. But since this already gives you a barrier, suppose this is alpha, some negative number, the values of the sequence will never get inside this neighborhood. So that means that, or up here, for that matter, this is minus alpha. And so that means that the sequence will not be convergent. But we know that the limit is 0, so that means that all the terms must have been non-negative to begin with. Otherwise, we will run into the situation where the sequence cannot converge. Okay, so this is one of the last things that we're gonna cover about series. The rest of the things, I mean, for the most part, are things that you've seen in Calc 2, and I'm just gonna leave them as exercises for you.